Okay guys, in this video we're going to be taking a look at how we can easily use synthetic division to actually help us evaluate a function for a given x value. That is to say, like, let's say I have a function on 33 here and f of x is equal to this pretty long third degree thing here. But what I want to go do is find out what's the y value when I plug 4 into this. And so the interesting thing is we could go do this. As a matter of fact, number 33 here, what I want to show you is if we wanted to go find f of 4, we could, as a matter of fact, everywhere we see an x, go ahead and take that out, and what we would do is we would directly substitute in a 4 everywhere we see that x. But I hope you can see how undesirable this would be to simplify in the first place. So what we're going to look at instead is a consequence of synthetic division, but it allows us to name a theorem after it. We call it the remainder theorem. So recall that the remainder theorem, what it says here is this: if the polynomial f of x is divided by this factor x minus c, which mind you is a first degree divisor, so cool, we get to use synthetic. But if you divide f of x by x minus c, then the remainder is actually equal to f of c. And so the remainder theorem, you know, if I'm going to write this anywhere, I'd say, I suppose the remainder theorem, if I were to write this symbolically, would say that, again, if we took some f of x, which is some polynomial here, and we divided it by x minus c. So again, remember that when you divide by x minus c, if you were to set x minus c equal to 0 and solve this, you would get x equals exactly c. So, of course, I would put c out here as my x value, but what it's saying is if you do this synthetic division, then the remainder that you get down here, not only is it any x value, it's actually the y value you get when you plug this into your function. So let's weigh the differences here and see how well I can do. One way we're going to do this is just with what we call direct substitution. Direct substitution. And then we're going to do this with synthetic substitution is what it's called. As a matter of fact, I'm going to leave that bar off there. So let's take a look at this here. Simplifying it, first of all, we would do our exponents. So let's see how long you can hang with me here. We got 4 cubed, that's 64. We got minus 11 times 4 squared, so that's 16, plus 7 times 4. I'm going to go ahead and write 28 and then minus 5 here. And then we'll say, well, 2 times 64, that's 128, minus 11 times 16, well, that'd be 10 times 16, 160 plus another 16. 160 plus 16 is 176. And we say plus 28 minus 5. Now, let's see here, 128 minus 76. You know what? I don't even know how comfortable I am with this. 128 minus 176 here. We're definitely going to end up with a negative 48. Looks like. So negative 48 plus 28 minus 5. I know these two give me a negative 20 here, and then minus 5, we get a negative 25. Whew. Okay, that's a lot of work, you guys, just to plug in a 4. You can see that when we evaluate polynomial functions here, it takes a little bit longer. And so because we do want to actually go make a lot of graphs of polynomial functions, which is going to include us making a lot of tables of values, we just want to be really good at evaluating given an x value. So we're going to be really good, you guys, at what we call the remainder theorem. And remainder theorem allows us to do what we refer to as synthetic substitution. So what's the difference between synthetic substitution and direct substitution? Well, synthetic substitution utilizes synthetic division, and the consequence that this last number right here actually is the y value at that x value. So what I want to look at here is let's excuse me, drop in my coefficients from my original polynomial here, from my f of x. And what we'll do is we'll put on the outside here the x value for which we're evaluating, which in this case is exactly 4, and we put exact x values out here. So you know how long it took me to do this. Let's kind of time it here. If I were to drop my 2, let's say 2 times 4 is 8. 8 plus a negative 11, no hurry, it's negative 3. 4 times a negative 3 is a negative 12. Negative 12 plus a negative 7, or positive 7 here is a negative 5. 4 times a negative 5 is a negative 20, and then finally I get negative 25. So two things. One, put a box around this, and right next to it we're going to say that this is f of 4. So to evaluate this function here, you can see that the remainder that I got was the exact same stinking remainder that I got over here with direct substitution. It's just that weighing my options here, synthetic substitution is way quicker than direct substitution. So when somebody asks you to use synthetic division and the remainder theorem to find the indicated value, they're just saying use your synthetic division array and the fact that the remainder is the y value at that x value. So again, let's take a look at, say, like a 34 here. If I were to look at, say, 34, first things first, we would drop in our coefficients of our polynomial. So we have a positive 1x cubed, a negative 7x squared, a 5x to the first, and a negative 6. And again, we want to put the exact x value out here for which we are evaluating, like our 3. And so let's go ahead and carry down our 1. We have 1 times 3 is 3. 3 plus a negative 7 is a negative 4. 3 times a negative 4 is a negative 12. Negative 12 plus 5 is a negative 7. 3 times a negative 7 here is a negative 21. And so that's going to leave us with a remainder of negative 27. Now the neat thing about our remainder is not only is it the remainder, you guys, it's actually f of whatever this x value is here. In this case, we say precisely f of 3. And so pretty neat consequence. We could say that on our graph here, it was very easy to find out that when we plugged in 3 for an x value, we got negative 27 for a y value. Cheers.